Hello, this is Jan van Heiningen, and I will talk about insar height-dependent atmospheric phase. At 3V Geomatics, we provide insar displacement monitoring services for clients around the world. We have developed an urban insar processing chain that can detect target displacement with high precision. To obtain accurate target displacement time series, contaminant insar signals must be modeled and removed. In the figure on the right, the topographically dependent atmospheric phase, which we call static atmosphere phase, has not been properly accounted for. Removal of this signal gives a cleaner time series as shown on the left. We use well-defined established models for the insar phase, which consists of several different terms to be estimated from the data, including the actual target displacement of interest and the height-dependent static atmosphere phase. We maximize the total coherence over a redundant network of insar interferograms to estimate the static atmosphere phase. We use the TensorFlow API to calculate the boxcar coherence. This is equivalent to taking the absolute value of the 2D convolution with a flat kernel over the wrapped phase. The leapfrog interferograms are formed from temporally adjacent SAR scenes. Here we define a transformation matrix DLF to IFG that we use to solve for the leapfrogs from any other network of interferograms. This enables us to write out the coherence maximization function to consistently solve for the leapfrog coefficients. Since the SAR is side-looking, this formulation also accounts for an incidence angle dependent correction factor. We can rewrite the coherence maximization to allow for a pixel-wise weighting based on the intrinsic SNR and a patch-based weighting based on the height variance with the convolution kernel. As a post-processing step, we convert leapfrog coefficients to per-scene coefficients. To prevent overfitting when there is insufficient topography, we introduce a regularization term in this step based on prior estimates of the leapfrog uncertainties and their expected magnitudes. Here we present a case study for Los Angeles. This image shows the displacement rate computed over an 8-year time span, consisting of the greater city area. The downtown area is indicated by the small magenta rectangle. The left image shows the leapfrog coefficients obtained for downtown and the greater city area. They are significantly different, reflecting the spatial dependence of the atmospheric phase. A seasonal trend can be observed in the per-scene coefficients, which is more prominent downtown than the wider city area. For the downtown AOI, we found that proper modeling of the static atmosphere phase resulted in fewer unwrapping errors and points being discarded in later post-processing steps. In summary, we have presented a coherence maximization algorithm with regularization that is robust and safe to use in most insar processing chains. Thank you for your attention and your interest.